This video is an introduction to multiple regression. So here we're going to be using more than one explanatory variable to predict a quantitative response. And the idea is that by giving more information in the model, you're going to be able to have more accurate predictions. So higher R squared, lower root mean square error, just more accurate predictions all around. So we're going to look at an example about car acceleration. You hear this talked about all the time in commercials, how long it takes to accelerate from 0 to 60. So what car features might explain faster acceleration? So faster acceleration here means a shorter acceleration time. The data set includes the weight of the car in pounds, horsepower, and acceleration in seconds for 392 different types of car. And we're going to think about two different models to predict acceleration. So the first is a simple regression model. This is what you've been seeing before. Simple just means that we only have one predictor in this model. So in this case, we're going to use only the weight of the car to predict the acceleration. And sort of the implied part, if you're using weight as your one predictor, is that you're ignoring all other variables. So there may be lots of other things about the cars that do affect the acceleration. You're not taking any of those into account in this simple linear regression model. So you can see the linear equation here with the y-intercept and the slope. So if we want to interpret that slope, we would say that as weight increases by 1 pound, the acceleration is predicted to decrease, right? Because this is a negative slope. Decrease by this amount, so by 0.0014 seconds. So this is actually surprising, right? Because this is implying that cars that have higher weight actually have faster acceleration, which that's not what we'd expect. We'd expect that if the car is heavier, that it would take it longer to accelerate. But it may not be a straightforward cause and effect relationship like this, right? We have to consider in an observational study that it could actually be due to confounding. So what could be a potential confounding variable for this relationship? One thing could be the horsepower, right? So it could be that the higher weight cars also tend to be higher horsepower. So there's a connection here. And then the higher horsepower is actually what's leading to the faster acceleration. So remember, anytime you have a confounding variable, it needs to be linked to both the explanatory and the response. So this seems like a reasonable explanation here, right? Heavier cars tend to be more powerful, right? In other words, they have more horsepower. Heavier cars tend to be more powerful, and that's what causes the faster acceleration. So it's not actually the weight itself, it's just that weight is linked to another indication, right? Power. So up until this point, we've kind of just like stopped there, right? If there was a confounding variable, we just say, oh, well, there's confounding, we can't make a cause and effect conclusion. But there is something analytically that we can do to understand this relationship better. We can take that confounding variable and include it as part of our model. So here you can see the expression for a multiple regression model. So it has BO, that's the, or B0, I guess, that's the intercept. But now you have multiple predictor variables. So X1 and X2 are both predictors. So you have multiple predictors, and each one of those comes with its own slope, right? So you have X1, which in this case is weight. There's a slope associated with weight. And then X2, which in this case is horsepower, and there's a slope associated with horsepower. So when we fit this model, we get different coefficients. So let's go ahead and interpret the slope related to weight again here. So as weight increases by 1 pound, acceleration is now predicted to increase by 0.0023 seconds. So I think that's more in line with our intuition, that heavier cars actually take longer to accelerate. But we also have to acknowledge that we have taken horsepower into account in this model. So we're going to add a little tag here at the end, holding horsepower constant. Sometimes you'll also see things like controlling for horsepower or adjusting for horsepower, something like that, but something to acknowledge that you're taking horsepower into the model. So what does it mean to hold horsepower constant? Basically, it means that we want to consider cars that have the same horsepower or close to it, and then for those cars that all have the same horsepower, we want to think about the relationship between weight and acceleration. So in this graph here, you can see that they are different categories of horsepower. So like the blue dots here represent low horsepower cars, and you notice that they do tend to be towards the left side of the graph, so they do tend to be lighter in terms of weight. So for all of those sort of light, low horsepower cars, we can look at the relationship between weight and acceleration for those cars. Right? And then each line is showing within each group, within each horsepower level, what does the relationship between weight and acceleration look like? So even though you have this negative relationship overall, if you stop and break it up into different horsepower levels, you'll see that within each one, there's actually a positive trend between weight and acceleration. So we can describe that by saying that there is a positive relationship between these things, a positive relationship between weight and acceleration. So that means the heavier cars take longer to accelerate. So there actually is a positive relationship between them, as we expected, after controlling for, so I'm using another one of those phrases there, after controlling for horsepower. So basically, once you break it down by horsepower, look at just one horsepower level at a time, then you can see that positive relationship. Okay, so that's our interpretation of the slope. It's very similar to what we've done in simple regression, except that we're adding this tag, holding horsepower constant, controlling for horsepower, adjusting for horsepower, something like that. What about the intercept? So usually the intercept is what you get when you plug in 0 for your explanatory variable, right? That would make this term go away, and you would be left with just the intercept. So now to get the intercept, we need both of these terms to go away, x1 and x2. So we would have to plug in 0 for both of those. So the interpretation of the intercept is that it would be the predicted acceleration, that's our response variable. This would be the predicted acceleration for a car that, let's see, 0 for x1, that's the weight. So it'd be a car that weighs 0 pounds, already pretty hard to imagine, and has 0 horsepower. So not really a car at that point. Okay, so definitely in this case, this predicted value, it says, is 18.4358. That's our intercept. But this is not meaningful in this context. So this is going to happen even more often in multiple regression because a lot of times if you look at all of your predictors equal to 0, it's either not going to make sense or it's not going to be a value that's included in your data set. So multiple regression is great because it can give us more accurate predictions. It can give us a way to control for our confounding variables. We just have to adjust our interpretations a little bit to match the new model.